Video, we're going to start section 3.6, and we're going to tackle the derivatives of inverse functions. And there's 3 bullet points here. We're going to find the derivative of an inverse function, differentiate an inverse trigonometric function, and review all the basic differentiation rules for all the elementary functions that we've covered so far. But first, what is an inverse function? Remember, if it passes the vertical line test, it's a function, and if it passes the horizontal line test, it will have an inverse function. And here we don't have the functions to go with it, but just the darker black line is our function f of x, and the lighter gray line is the inverse function, f inverse of x. And you see that every point on the original function, a comma b, if we reflect that across this red dotted line, y equals x, we flip the point around. Here on the original function, it's a comma b. Here on the inverse function, it's b comma a. Because, remember, a is the input of the function, b is the output. The inverse function reverses the process. So now b is the input and a is the output. So, the derivative of an inverse function. The next 2 theorems discuss the derivative of an inverse function. The reasonableness of Theorem 5.8 follows from the reflective property of inverse functions, as shown in figure 5.1.2. And that's the one I just showed you on the previous slide. Proofs of the 2 theorem are given in Appendix A. And here, Theorem 5.8 just gives us some points about continuity and differentiability of a function and its inverse. So we're going to let f be a function whose domain is in an interval capital letter I. If the function has an inverse, then the following statements are true. If the function f is continuous on its domain, then its inverse function is also continuous on its domain. If the function f is increasing on its domain, then the inverse is also increasing on its domain, and it works for decreasing. If the function is decreasing, then the inverse is also decreasing. If f is differentiable on an interval containing some point c, and the derivative f prime of that point c does not equal 0, then the inverse function is also differentiable at that point. And Theorem 5.9 talks about the derivative of an inverse function. Now this might get a little confusing. Hopefully I'll flip back to that picture and that might clear it up a little bit. Let f be a function that is differentiable on an interval I. If the function f has an inverse function g, so g is the inverse function, then g is differentiable at any x for which f prime of that g of x does not equal 0. Moreover, the derivative of the inverse, g prime of x, is just the reciprocal of the derivative of the original function, as long as, this f prime of g of x does not equal 0. Again, let's see if the picture can clear it up a little bit. Back to here, the original function has a point input a, output b. The reflectant, or the inverse function has the reflection of that point. The input is b, the output is a. Now, if we think about slope that this Theorem 5.9 is talking about, here we would have, if I drew a tangent line, let's say that this slope is 4. The slope at this reciprocal point, this inverse point here, would be the reciprocal of this. This is 4 over 1. This slope would be 1/4. The slope at those reflected points are just inverses of each other. That's all this Theorem 5.9 is saying. If I had the slope here at this point, and I wanted the slope here on the derivative, I would just take its inverse. I would flip it over. And we'll see that play out in example 5 here. So we have our given function. F of x is 1/4 x to the third plus x minus 1. And in part A, they're asking us, what is the value of the inverse when x is equal to 3? So what we want to do is take our original function, 1/4 x to the third plus x minus 1, and we want to figure out what number do we put in for x that we will get an output of 3. Because here we're talking about the inverse, and we want to put a 3 in there as its input, so we want to figure out, in this original function, what value of x gives us this output of 3. And this is an easy one. We can just, a little trial and error. This is f of x If we plug in f of 0, we'd get 0 plus 0 minus 1, or negative 3 equals, or negative 1 equals 3. That's not true. So we could try f of 1. 1/4 plus 1 minus 1 is a fourth. 1/4 does not equal 3. Let's try f of 2. So 2 to the third is 8. A fourth of that is 2. Plus x would be another 2 minus 1. 2 plus 2 minus 1 is equal to 3. So here's the point that we're interested in. On the original function, f of 2 is equal to 3. Or we could say the point 2 comma 3 is on the function f. So they're asking us here, what is the inverse function when our input is 3? Well, remember this is our original function, we put in a 2 and out comes a 3. If we reverse that point for the inverse function, f inverse of x has the point 3 comma 2 on it. And that's what they're asking us here. What value comes out of the inverse when we put a 3 in it? Well, out pops a 2. That's our answer, 2. And the part B. Now they're asking us about the derivative, something about the slope. So it says, what is the value of the inverses, f inverse prime, of x when x is equal to 3? So first, let's go back to our original function. F of x is our 1/4 x to the third plus x minus 1. And let's take its derivative. F prime of x would be, bring down to 3 and multiply, 3/4 x squared plus 1, and then that minus 1 would derive right off. So we know we were interested in, again, for our original function, f of x, the point 2 comma 3 was on it. For the inverse, f inverse of x, we had the point 3 comma 2. So to find the slope occurring on the inverse function when x is 3, we can take that reciprocal point and plug it into the derivative of our original function. So f prime of 2 is going to be 3/4. 2 squared is 4 plus 1. So that would be 12/4, or 3 plus 1 equals 4. So again, this is the original function on f of x. If we are looking at the x value of 2, we know at that point our slope is equal to 4. Slope of f of x. So to find the slope of f prime of x at that reflected point at 3 comma 2, we just flip this over. This is 4 over 1, so the slope at the point we're interested in is 1/4. It's as easy as that. And here's a little picture to sort of back up what we just did. In example 5, note that the point 2, 3, at the point 2, 3, the slope of the graph of f is 4, and at the point 3, 2, the reflected point, the slope of the inverse function, f inverse, is 1/4. This reciprocal relationship, which follows from our theorem 5.9, can be written as shown below. If y equals g of x, which is our inverse of x, then f of y is equal to x, and f prime of y is dy dx, the derivative of x with respect to y. Theorem 5.9 says that the derivative g prime of x is dy dx, which is the same as 1 over, we're inverting that, f prime of g of x, and that g of x we're just going to replace with a y, or 1 over dx dy. We just flip it over. Dy dx is 1 over dx dy. And again, here the darker color graph is the original function. The point 2, 3 is on it. The lighter gray line is the inverse function, f inverse of x. Point 3, 2 is on that. We figured that out in part A. And then in part B, we looked at the slope. We found this slope here occurring at point 2, 3. That slope was 4. So for the inverse, we just flip it over, 1/4. So example 6. The graphs of inverse functions have reciprocal slopes. Hopefully this is just going to, hammer home a little bit more of what we just talked about in that previous example. So our function, f of x is x squared. F of x is x squared. And we're only looking at positive x's greater than 0. And of course, what is the inverse of squaring something? Well, that's square root. F inverse of x is the square root of x, or x to the 1/2. And they're asking us to show that the slopes of the graphs of the function and its inverse are reciprocals at the following points. So here's the point 2, 4, and its mirror 4, 2. And then we have 3, 9, and 9, 3. So before we do anything, I'll switch over to blue here, and we'll take the derivatives. This will be f prime of x. So the derivative of x squared is just 2x. And then over here, we're going to have f inverse prime of x. The inverse's derivative. And for x to the 1/2, that would be 1/2 x to the negative 1/2, or 1/2 times the square root of x. So there is our function and its derivative, the inverse and its derivative. And let me switch over here to red. Let's see here. For part A, we want the slope at the point 2, 4. So to find the slope here at 2, 4, we plug that x value in. So we get f prime of 2 is equal to 2 times 2, or 4. Now if we take the flipped point, 4, 2, and we plug that here into the inverse, f inverse prime of 4. So we're going to plug in a 4 for this x. So this x is replaced with a 4. The square root of 4 is 2. 2 times 2 is 4. We have 1/4. And again, these are reciprocals. 4 and 1/4 are reciprocals. And let's check out B, 3, 9, and 9, 3. So for part B, the slope at the point, this would be 3, 9. So f prime of 3 is just 2 times 3. And 2 times 3, of course, is 6. So we know that when we plug in the reflected point into the inverse's derivative, we're going to flip this over. Instead of 6/1, it will be 1/6. So let's see here. F inverse prime of 9 is 1/2 times that square root of 9. And the square root of 9 is 3 times 2. 2 times 3 is 6. So we do get the 1/6 that we were expecting to get. There are the slopes, and they are, of course, reciprocals. And I think we do have a picture to go with it. So here is the squaring function. And remember, we were just dealing with the positive x values. So this is our half of an upward opening parabola. And if we put in 2 and we square it, we get the 0.4. If we plug in the 3 and square it, we get the 0.9. So 2, 4 and 3, 9 are points on our original function, the squaring function. And then here in lighter gray, we have the square root function, the inverse. If we square root 4, we get 2. If we square root 9, we get the output value of 3. And then we can see also where those slopes line up. Here, the slope at this point was 6, pretty steep. At the reflected point on the inverse function, the slope was much flatter, and it just turned out to be its reciprocal, 1/6. Same here, we had a slope of 4. Here our slope is 1/4.